Um, all right. It's time to join the resistance. Get it? It's a circuit joke. Alrighty, let's go ahead and get started with our square of love notes. So these notes are going to help us figure out how to solve for certain values within circuits. Those could be series circuits or parallel circuits where there are more than one resistor. And the first one we're going to start off with is this series circuit above. And our example here says draw a series schematic diagram that contains 3 resistors, 2 ohms, 4 ohms, 6 ohms, and one 24-volt battery. So up above, we have our circuit. We have R3, R2, and R1. And let's just say that R1 is 2 ohms, R2 is 4 ohms, and R3 is 6 ohms. So let's talk about a few rules, though, before we dive into this. First thing is that when we're dealing with series circuits, the total resistance of the circuit is just going to be us adding up the resistance of each resistor. So in this case, we know that R1 is 2, R2 is 4, R3 is 6. So the total resistance that this circuit has is 12 ohms. Next, we want to figure out the total voltage. So in other words, how much energy is that battery supplying? Well, the total voltage is going to be equal to the voltage that R1 is using plus the voltage that R2 is using plus the voltage that R3 is using, which really just means that the total voltage of the battery is being split between all 3 of those resistors. Lastly, we have current, and a nice property about series circuits is that the current is going to be the same everywhere in the circuit. So the total current is the same as the current flowing through resistor 1, which is the same as the current that flows through resistor 2, which is the same as the current that flows through resistor 3. Current is the same everywhere in series. Voltage is going to be different for each resistor. Now let's get to the math. And let's talk about a few steps about using the square of love. So down below, we have the square of love. And the square of love is just really a weird way to show all of our information in a circuit. On the top, we got VIR, voltage, current, resistance. And on the left-hand side, we have our components. So all of our resistors and then the total for the circuit. First step is going to be to plug in all of our known values. We know that R1 is 2 ohms. We know that R2 is 4 ohms. We know that R3 is 6 ohms. Next, let's take a look at the voltage. Well, in a series circuit, the voltage is going to be the voltage supplied by the battery. And in this case, it told us that we had a 24-volt battery, so our total voltage is 24 volts. And then we can't forget about the resistance, and we said that the resistance for the circuit, or our total resistance, is just us adding up all those resistors, which gives us 12 ohms. The next step is that we want to use V equals IR. And again, that's just Ohm's law. And we can use that if we have 2 out of 3 values in one of our rows. So this is another Sudoku / tic-tac-toe type thing where we need to fill out one row until we can move on to the next one. And if we're only missing one thing, then we can fill it out. But if we're missing 2, we don't have enough information to do that. So the only one that we can find right now is the total current. The equation we need to use is voltage equals current times resistance. Therefore, I have V equals IR, which is really just 24 equals I times R. R meaning the total resistance because I'm using the total voltage. If I divide, I find out that the total current should be 2 amps. So I go ahead and plug that in there. Now the last step is just to apply those rules that we talked about on the last slide. In series, we said that current is the same everywhere. So since my total current is 2 amps, that means the current flowing through resistor 1 is 2 amps. The current flowing through resistor 2 is 2 amps, and the current flowing through resistor 3 is 2 amps. Now I need to figure out the voltage. Well, I'm only missing voltage, so all I have to do is use my equation, V equals IR. The current for resistor 1 is 2. The resistance for resistor 1 is 2. 2 times 2 is 4. I do the same thing for R2. 2 times 4, that's 8. Same thing for resistor 3. 2 times 6, that's 12. How do I know if I'm correct? Well, on the last slide, we said that the total voltage equals V1 plus V2 plus V3. So if we add all those up, we should get the total voltage. So 4 plus 8 plus 12, that gives me 24 volts. So I know I'm correct. Now let's take a look at a parallel circuit. And below, we have a parallel circuit with the following resistors. R1 is 2 ohms, R2 is 3 ohms, and R3 is 4 ohms. And now we have a battery that is only 6 volts. So the first rule for parallel is that the total resistance can be found by using this equation. 1 over RT, RT stands for total resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R, etc. You'll notice that this equation is different than the series equation. And what this equation really tells us is that the total resistance will always be smaller than any other resistor in parallel. So if we use our numbers from above, we find out that 1 over RT is equal to 1 over 2 plus 1 over 3 plus 1 over 4. If we don't have a calculator, we'll find the least common denominator. We add them all together, and we find out that 1 over RT equals 13 over 12. Remember though, we're solving for total resistance here, not 1 over total resistance. So now we have to flip both sides, and we end up with the total resistance is equal to 12 over 13. If we simplify that, we find that our total resistance is 0.923 ohms. The next rule is that in parallel, the total voltage is equal to the voltage of resistor 1, which equals the voltage of resistor 2, which equals the voltage of resistor 3, which just means that the total voltage is the same for every single resistor. And we knew this before when we had our light bulbs. We said that our light bulbs were each drawing the same amount of voltage from the battery. They got the same amount of energy. And that's a property of parallel circuits, is that voltage is the same for everything in that parallel circuit. But current is different for everything in that circuit. And the total current is equal to the current of resistor 1 plus the current of resistor 2 plus the current of resistance 3. So important things to remember is that when we deal with parallel circuits and we add up the total resistance, it's 1 over. When we are talking about voltage with parallel circuits, we need to remember that the voltage is the same everywhere. And lastly, current is going to be different. The current across each resistor is going to add up to the total current that the battery is supplying. Let's take a look at the math behind this now. First step, plug in all of our known variables, just like before. R1 is 2 ohms, R2 is 3 ohms, and R3 is 4 ohms. The total voltage is 6 volts. Next, we want to apply the current voltage rules for parallel that we talked about on the last slide. We know that voltage is the same for everything. So the total voltage is 6, meaning that the R1, R2, and R3 each have 6 volts as well. Once we have this information, we can use it to solve for current. So when we have 2 out of 3 values in one row, we can just use Ohm's law to solve for the missing value. So the first row there, we have R1, which is 2 ohms, and the voltage through R1, which is 6 volts. Plug that into our equation, 6 equals I times 2, solve for I, and we find out that the current here is 3. We repeat and solve for R2, 6 divided by 3 gives us 2 amps. Now we do R3, 6 divided by 4 gives us 1.5 amps. To find out the total amps that are going through our circuit, we just add all of the currents up. 3 plus 2 plus 1.5, that's going to give us 6.5 amps. Lastly, we have resistance, and we could solve for this 2 ways. We could use that really difficult equation on the last slide, or we could just use Ohm's law to figure out resistance. and Ohm's law, V equals IR. 6 is our total voltage. Our total current is 6.5. So we solve for R, and we get R is equal to 0.923 ohms. All right, let's quickly summarize what we talked about. So in terms of series circuits, important things to know is that the total resistance can be found by just adding up the resistance of all of our resistors. And the total resistance for series will always be the biggest resistor. Current is going to be the same everywhere in that circuit. And the total voltage is going to equal the voltage of each of those resistors added up. So in other words, the total voltage is the sum of all of the voltages. For parallel, the total resistance can be found using this equation, which is the same one we did before. I'm just trying to simplify it for you. And that just says R1 to the negative first, which is the same as saying 1 over R1. If you plug it in just like this in your calculator, you should be able to get the answer right, no problem. The total resistance will always be the smallest resistor for parallel. Voltage is going to be the same everywhere for parallel. And lastly, total current can be found by adding the current of each individual part of the parallel circuit up. Or in other words, total current is the sum of all of the currents inside the parallel circuit. The reason the total resistance in series gets bigger and bigger is because these resistors in series are only sharing one line to the battery. And because there's only one path, the more resistors we stack up on that path, the harder it is for those charges to get through. A series circuit is like if I were to stack up one piece of paper and have you run through it. Now I'm going to stack up 100 pieces of paper and have you run through it. The more paper that I stack up, the more resistance. So let's think back to when you guys were in school and we were all in the big gym. After a big pep rally or whatever, we all wanted to go home and the school only had one door open. Well, with only one door open, that's a lot of resistance. But if we think about this in terms of a parallel circuit, what would happen as we added more and more of these paths to our circuit? Because with parallel, you need more paths in order to have more resistors. Well, we could think of another path as another door opening for that auditorium. And the more paths we have, the more doors we open. What's going to happen as we open up more and more doors? There's going to be less and less resistance, which means that people are going to be able to get out of the auditorium a lot easier.